As Monica introduced me, my name is Ro. I am from Duke University. This was sort of the culmination of one of my courses called regression analysis. It was an intermediate statistics course in which I wanted to explore the effect of weather conditions on short and long distance running performance. So let's just get into it. I guess to give some context for this research project, going into it, I was training for a marathon at this time, had been spending a lot of time thinking about running performance and the different effects that it can have. And I was also spending a lot of time just kind of like looking online and Googling things, and I figured that I would spend this time more productively and maybe use a project out of it. So this is some of the previous research that has been done in the field. It was primarily done for sort of marathon running performance, in which we found that a lot of increased temperature is associated with slower running times. This was actually quite counterintuitive to me personally, because running in the heat and running in the cold seemed almost equally miserable, but it turns out that running in the hot weather decreases your time more significantly. We also see that things like humidity and wind speed play off of air temperature and often exacerbate any effects that it has. So for example, increased humidity during hot weather make any effects of the hot weather even worse. Similarly, wind speed kind of has a mixed effect on running, where headwinds can diminish performance, where tailwinds can improve performance. So this was kind of the context that I was going into, and found that there were a lot of gaps in regards to both short distance running performance and then how they kind of interacted together. So this kind of led to my research question of how does the relationship between air temperature and running performance depend on race length for elite runners? Going into this question, I had kind of found a data set that looked at running performance across a bunch of different competitions. I guess you can imagine it as though each row is a competition event by gender. So one row would be 5K Women's Olympics 2019. And then you would have 3 columns for sort of first place, second place, third place. And this data set gave a unique opportunity to kind of look at the weather during that particular competition, usually the average across that whole period of time, and also the sort of effects on what happened to the runner's performance at the end, because we see the times. To give a quick overview of some of the variables that I was looking at was, first, I was looking at weather variables, including air temperature, adjusted wind speed, relative humidity. I guess of important note is that the most important variable here is air temperature, considering the focus of the question. But I wanted to be able to control for other weather variables, considering what the previous literature had shown on how different weather variables can mix together. I guess another thing to keep in mind was that I was really worried about multicollinearity with weather variables, just because oftentimes you can kind of have some really similar things in the sense that you have adjusted wind speed and you have wind speed. So this is kind of like the reason why I went into thinking about these particular variables to avoid some multicollinearity issues. We also had some data on the background information. So this includes things like race type, sex, and year. And this leads to another point that I made while trying to define my model and think about what exactly I wanted to study. While there were a large variety of races within this data set, for example, we had the mile, we had the 10K, I really wanted to compare short and long distance running. And a couple of considerations that I made, for example, for the 5K over the 1 mile, is that both the 5K and the marathon traditionally take place outdoors. And they're really, really common within all major events. So the Olympics and I think like the Goldwater. Either way, things like the mile and some ultras don't quite have that same consistency across all competitions. And so I ended up narrowing it down to 5K as my short distance and marathon as my long distance. Another kind of consideration that I made here is that the aerobic and anaerobic needs of each each race type is different for these two, significantly enough that I thought it'd be reasonable to compare. And I guess for people who are maybe a little less familiar with running, I guess at the elite level, 5Ks will usually take below 15 minutes. And and marathons will take around 2 hours. So it's a really significant difference of how long you're just staying outside and exercising. So one of the biggest considerations also that I made was, how am I going to measure running performance if I want to compare it across short and long distance lengths? As I previously mentioned, the times that you spend are pretty significantly different. So it's very hard to compare a 30-minute time versus a 2-hour time, et cetera, et cetera. In order to get over this issue, I created this new variable that I called world first percentage, where I take the world record, I subtract it by first place time, and I divide it over by world record time. And the thing that I'm trying to accomplish here is essentially making it so that I'm going to get a percentage value of how much the first place time is of the world's time in terms of difference. When we go into the results, it'll become a little bit clearer. But the idea is just that we can have a percentage value to compare across different races. I don't have it on these particular slides, but I actually found that for both the 5K and for the marathon, the distribution of world first percentage was relatively similar, enough so that I felt okay with comparing it. Going into sort of my model specification here, the coefficient of interest here is beta 3, where I'm taking the interaction term between air temperature and race type. And in doing so, I'm able to see how air temperature differentially affects 5Ks versus marathons. You'll also notice, I just kind of added covariates here. There were a couple of things, as we mentioned before, which include things like weather variables, and also included things like just basic race background information, such as sex and year and that kind of thing. So these were the results of the model. It's a lot of information, but actually the only coefficient that we're particularly interested in is this last estimate on the last row here, negative 0.0019, and we had a p-value of 0.0009. So going into some interpretation of this, and hopefully this is where the sort of dependent variable that I made becomes a little bit more clear. I found that for a 5K, each 1 Celsius increase in air temperature, the first place percentage of the world record is expected to decrease by 0.001397%, controlling for all other variables. So we can kind of pull back and think about this a little bit. We can imagine that for the marginal increase in air temperature, my performance as a runner is going to differ from the world's records by 0.00139% slower. So I'm going to become slower with each air temperature increase. I guess to put this in more concrete terms, if we imagine that the 5K world record was 12 minutes and 30 seconds, I think this is a number that I pulled off from a given year, then 1 degree's increase in air temperature is associated with the first place runner being 0.001 seconds slower than the world record. Again, for those a little unfamiliar with the running world, this is like quite significant, especially considering the fact that at these elite races, the seconds and milliseconds really matter, and this is only for a marginal 1 degree Celsius increase in air temperature. For marathons, we find that the expected decrease is larger at 0.002%. And I guess pulling it back into real life, if the marathon world record was 2 hours and 10 minutes, again, a number that I think I pulled online from an actual race, then the 1 degree's increase in air temperature would result in the runner being 0.15 seconds slower than the world record. Again, within a racing setting, 1 degree Celsius is very minimal. You can imagine that within a race, if you're taking in Australia versus in, I don't know, somewhere in London, you can have differences of up to 20, 30 degrees, and it will affect these two differently by this percentage. And the way that I've created this sort of outcome variable is such that I want the 0.001% to be comparable to the 0.002%. And in fact, we can see that the percentage of difference is greater for the marathons, meaning that the marathons are going to be more slow than the 5Ks for a given increase in air temperature. So I guess I will quickly run through some of the limitations of this. It didn't provide runner IDs, so we're a little bit worried about independence, considering that this is a linear model. We use complete case analysis to deal with missingness. We felt it was reasonable to assume missingness completely at random. So it resulted mostly in a loss of power without biasing any results. Of course, these are observational data. We cannot directly conclude that hot temperatures result in differing race outcomes. I will kind of default to sort of previous literature to support me on this. And finally, that it is primarily elite runner data, so we can't generalize these results. So just as a final conclusion, we, in this paper, introduced a novel statistic based off of individual performance relative to race-specific record-setting paces. And we ultimately suggested that the difference of temperature's effect on running performance is significant between marathon and 5K runners, where increasing air temperature was associated with worsening running performance in marathon versus 5K. I also want to take a quick moment to thank my mentor, Yu Jiang, for all of his support across this process. And yeah, thank you so much for having me.